Well, we'll start today the lecture for three-phase transformer. So if you understand single-phase transformer, three-phase transformer will be easy. And do we need three-phase transformer? Of course, we need three-phase transformer. Because if you go, we have load, the three-phase load. So how you supply? You need three-phase transformer. When you and power station does not supply power to the consumer or building in a single-phase transformer. Three-phase transformer, huge. If you have the chance to go to Georgia Power or any substation next to the city, you'll find this transformer are really huge, and they are cooled by oil, and the windings is really thick, because I mean you're talking about 100 amperes or something like that. And that's why when you do the equivalent circuit for three-phase transformer, usually we ignore the resistance and only concern the reactance, because you know the Z equivalent of the transformers R equivalent plus JX equivalent. We just make it zero. It's not zero, but it's just compared to X is nothing, because it's thick wire, so the resistance is really nothing. But the reactance is more effective. So what do? There are two ways. You can have three-phase transformer, like have one coil with three legs, and you can have three single-phase transformers. You get three single-phase transformers and they connect. That's on the way. And then the connection is three-phase. So you can have delta or star or Y connection. So you will have variety of transformers. So I show you here, I mean, you can have Y delta. What is Y delta? The primary is Y connected, and the secondary is connected as delta. You can have Y delta, delta Y, delta delta, YY. There are some common connection or configuration that are used with three-phase transformer, and some they are not popular and they rarely we find. So we'll talk about that. So if you have a chance to work at Georgia Power, you have idea about that. That's the connection. That's the three-phase. No, I'm sorry. Three single. There's a difference between three-phase transformer and three single-phase transformer. What you have here, you have that single-phase, and now I'm going to show you how you connect it to be three-phase. Okay, so that's called three single-phase transformers. And all the connection here that explain this table, I'm going to show you one. Here you go. That's one. You have the winding. You can connect it to star by connecting the whole second end of each coil. I hope that I have one. Oh yes, here you go. So how you do if you want to make like a star delta? So you want to connect, and that's a famous one. So you get the one. Observe the dot here. What does it mean, dot? Dot, it means that if it's positive with respect to this one, so that will be positive with respect to the undotted. So the corresponding on the secondary will be the same polarity. So they put the dot so you know where is the positive. Of course, it's not DC, it's AC, but where is the life, where is the neutral? Because I mean, if you have cycle like that, positive, negative, and let's say that you will have, so when this is positive, that's will be positive. When it's negative, negative. But if you change the polarity here, so it means when it's positive here, it'll be negative cycle here, flip. Because I mean, that's show you where the polarity, they are the same. Okay, so let's just go and do the connection. So how you connect star? That's one phase, you get that outside, and the second phase, you get the whole dotted out, all right? And for the neutral, you will connect the end, this end, with this end, with this end, and you call it the neutral. So that's, you know, you get the, okay, so that will be the primary. How you do delta? All right. When you want to know the connection of the delta, let me just show you something here, an easy diagram. That's the delta. That's the star. That's what I did. I connect the old end. If you have 1, 2, 1, 2, 1, 2, 1 is the dot, 2 undotted. You connect the all undotted, 1 point. That's the neutral. And delta, you have here 1, 2, that's one terminal, that's second terminal. Then you connect the first terminal to the second of the following one. You connect one of phase A, you can say you connect A1, let's say that, to this point, which is called B2. And you connect, okay, let me just write A1, you connect it to B2. And then B1, you connect it to C2. And C1, you connect it to A2. So you connect the beginning of the winding to the end of the following one. So I mean, when I was student, I tried to do so. I said like A, B, C, and then I wrote A, B, C on the opposite direction. So you see, that's A, B, C, and this A, B, C. Then you put 1, 1, 1, 2, 2, 2, and then I know what I'm connecting. Let's do that with diagram. But this is the actual one I'm going to show you now. That's how you can connect it. That's a small. We agree with the textbook that you are using that the secondary will use the lowercase and the primary uppercase. So now to understand, I will write A, B, C as we agree, and then we'll put 1, 1, 1, and then I put in the other direction A, B, C. I put 2, 2, 2. Just remember. So
wait, that's not right.
It's not right, yeah. That's not right, yeah. Okay. All right, yeah. So let's see how we connect this one. So that's A1, and that's A2, and that's B1, and that's B2, and that's C1, and that's C2. A1, A2. So I connect A1 to what did you say in the other diagram? We connect the first to the end. So the A1 connected to B2, right? And this one to this one. And C1 to A2. And then you get the output from A1 and B1 and C1. That will be your point, A, B, C. That will be your output. And that's, I mean, how you connect it. But this diagram, of course, is like, it's easy as, it's just, you can see like that. But I'm showing you practically when the transformer, we have it, how we do it. We do that, we'll get this one. And we make sure that everyone, the beginning connect to the end of the following one, and so on. And that will be the delta. Okay. Well, that's how we connect it. What is the difference between each? I'm going to show you, I mean, how we calculate the magnitude. But let's see, I mean, the practical point of view. First, the rated value, the apparent power of the transformer that connected like that will be 3 times the single phase, of course. Like if you have 3 single phase transformer, and let's say, for example, each transformer is 10 kilo VA. So the total power will be 3 times 10 will be 30. That's number one. So obviously, I mean, it has great high rate value of the apparent power. Okay. Now let's look for the voltage rating. What about the voltage rating? It depends on the connection. Are you connected Y or delta? I'm going to show you. Sometimes if it's connected delta, so the line voltage equal the phase voltage, as you know. But if you connect star, so the line voltage would be squared 3 times the phase. And that would did in 3 phase. But let's see the connection. Why delta connection? That's usually the most application when they use it. They use Y delta to step down a higher voltage to a lower voltage. When they want to step down, they use Y delta. So they put Y on the high voltage side and delta on the lower voltage side. And the neutral point on the high voltage side can be grounded. You can connect to the ground. So if there is fault, when you study power system, when there is fault, so the current they are collected or summed to the neutral and go to the neutral. So what is the application again? Y delta, when you want to lower the voltage, and there are many applications. For example, I mean, when you the power is transmitted from the power station to the transmission line, as you know, the increase the value of the voltage. So they used step up. So if let's say that if 380 volts coming out, then they make it like in kilo voltage. So the transmission line voltage is really high voltage. We're talking about 11 kilovolt, 33 kilovolt, high voltage. Why do you do that? To minimize the loss. Because I mean, you transmit the power long transmission line. We are talking about, thousands of miles. So it would be big power loss. So to do that, the increase the voltage, there is a voltage. So the voltage will be high and the power loss get low. Well, so they use, then when we go to the consumer, the voltage of the transmission line is high, 11 kilovolt. It's impossible to get 11 kilovolt to your home or to the building. So they get to lower it. So go to some place called substation. And this substation is like has 3-phase transformers with protection, breakers, and things like that. Then there's the transformer lower the voltage from high voltage to low voltage so we can use it because it's already transmitted. So now we want to use it. So you don't use kilovolts, use a normal voltage like 110 volt of single phase and then square root of 3, that would be like 208 line phase as you have in the lab. So that's the main transformer using in this application. Then you have the other one, delta Y. That's to step up voltage. That's where from the power station to the transmission line. So if I can sketch something like that, if this is the power station and has a voltage, and then the transformer here to increase the voltage or step up the voltage, what type they are using to step up the voltage? Delta Y. And then you have here the transmission line. That's the high voltage. And then you go there to another transformer that will be Y delta, and that's where the substation, then you go, that's here the load, the consumers they're using. So that will be step down, and that will be step up. All right. So that's the way they are going to connect. Well, there is delta transformer. You can make delta. Then one transformer can be removed. That's what's the advantage of it. They are 3 single phase transformer. The advantage of delta, if there's a problem with one phase, they can remove one phase to fix it and leave the other 2 phase and still working. So that's the advantage. So they used in places where they be like reliable. They can fix it, and so we call it open delta. I'm not going in the details because if I'm talking about the power transformer and the application and the analysis, you can take the whole semester. So there's so interest in power, we will get the stuff, but I want to explain the basics of the 3-phase transformer. But you got to know the application. Why? Rarely used, very rare that be used, because they have problem with the exciting current, that the magnetization in the transformer, and induced voltage. Also, that's can be studied in power and studied in harmonics, something like that. They have problems with the induced voltage. Well, so these are the connection, and I show one connection, and we want to know how can we analyze the power transfer. Okay. Well, there are many connections. I'm going to choose Y delta, and whatever I'm going to do with Y delta, you can do it in any other connection. You can do it in delta Y. Okay. So Y delta, I will sketch the easy one. Let's say this is Y on the primary. And on the secondary, let's say we're having delta. Intentionally, I'm going to sketch it like that, and I'll tell you why. So it's delta, still delta. And that's A, B, C, and the other side, maybe you're going to have the capital letter. That's A, B, C. Anyway, remember, each winding represents one transformer. Why the reason I did this delta in this way, I want to tell you, like, I mean, each winding of each transformer is coupled with the secondary. It's secondary. So I make it parallel so I can tell you that this one and this one, they are coupled, that they are parallel. All right. And this one coupled with this one, and this one coupled with this one. That's why I sketch in this way. Because the original, as I show you, is like three-phase transformer. So you know which winding. Anyway, how can you analyze it? Well, every single phase transformer has its own rated values, apparent power and voltage. Example, if you have a single phase like that, and you have the rated value given, like if you say that's 10 kVA, and let's say it's equal to 2000 over 200 voltage. So you can get the turns ratio. The turns ratio A is equal V1 over V2. But now we want to be careful. This transformer is a part of a three-phase. So that represents phase. So I'll write A is equal V phase 1 over V phase 2, which is equal to I phase 2 over I phase 1. That's for single phase transformer. And to be precise, that's the voltage on the phase 1, the voltage on the phase 2, the current in phase 1, and current in phase 2. And this is the S of one single phase. And now I'm going to connect them to delta star. When I are connected, I will show you the nice connection. I'm not going to make the, I'll make the practical one that we usually use as an engineer. I have one winding there in the star like that. And you have delta. Now let's find the relationship between each voltage. We know that A is the turns ratio of one single phase transformer. Keep this in mind because now we're working with three phase. And we said that that's the relationship. Very important to understand that this relationship of one single phase transformer. When you go for this connection and Y connection, we are going to say like I1 represent line current, an obvious line. And the voltage across from line to line, I'm going to call it V1. So V1 is the line to line voltage on the primary side. I1 is the line current on the primary side. And the same thing I'm going to do in the secondary. The current coming out, of course, to the load, that will be I2. And the voltage across from line to line on the output or on the secondary one, I call it V2. And remember all these vectors. All right. When I go now for the single phase transformer, that's one transformer. If we can, like, that's one transformer. And that's the corresponding secondary. So I want to find the turns ratio here. The voltage across the winding one, that's VB1. And the voltage across the winding here, it's V phase 2. And I know the relationship between both. It's A in front of me here. And the current in the winding here, it's I phase 1. And the current in this one is I phase 2. That's very important to do it in this way, not to make any mistakes, so be precise. Now, I want to find the relationship between voltage and current on the secondary side, the line values, and voltage and current on the primary side, I1 and V1. Simply, I want to find what's the relationship between V2, I2, and V1 I1. Very simple. If you just follow. If you have any question, interrupt me. I1, IB1. In this case, I1 is equal IB1, but I1 is the line current, IB1 is the phase current in general. Because if you go there, IB2 and I2 are not the same. But IB, IP, it means phase current. I, just without anything, line current. So now let's see, the relationship. I know that A, the main quantity that you know, A turns ratio of one single phase transformer is equal. Let's look for the voltage. Voltage phase 1 over voltage phase 2. And now see the relationship between V phase 1 and VL1. What's the relation between VP1 and V1? Obviously, V1 is the line is equal to square root of 3 times VB1, right? I know that from here, that V1 is equal to square root of 3, the phase voltage. That's in the star, we know that. If you forgot, just tell me and I'll refresh it. So I will replace VB1 by the equivalent V1 over root 3. What about the phase voltage on the secondary side? VP2, because it's delta, that point to this point is the same point here, and this point the same point here. It's the same thing. V2, all right, just let's say, to make it, everything's fine. Another voltage across the line, that's V2. From this line to this line, right? So this point here and this point you go there, so it's the same. And we know that. So delta V2 is equal V phase 2. So I'll write VB2 is equal V2. All right. So now I can say it's equal V1 over root 3 V2. I want to find the relationship between V1 and V2. Of course, I got it here. Let me just write A. I found A is equal V1 over root 3 V2. If you want to find V1 over V2, only multiply both sides by root 3. So root 3 cancel. So what's V1 over V2? Is equal square root 3 times A. So I'll call it A, like anything else, not the same thing, is equal to V1 over V2, which is equal to A times square root 3. And we got the relationship between the line voltage in both sides. What about the current? Well, I will prove the current, but it will make sense like the single phase. The single phase, they are opposite. A is equal VB1 over VB2. It's equal IB2, the opposite. So let me see. What's the relationship between I2 over I1? That's the line current. Let's look for I2. I2 and IB2, I2 is bigger than IB2 in delta by square root 3. So I2 is equal square root 3 IB2. Well, what about I1? I1 in star is the same as equal IP1. So I'll write IP1. So root 3, what's IB2 over IP1 from this equation? It's A, the turns ratio of the single phase. So just do it. Yes, I got what I expected, which is the other A. It's equal A times root 3. So I can write now A, line to line, it's equal A root 3 is equal V1 over V2 is equal I2 over I1. So we know the relationship between phase and line currents. All right. Well, let's now solve one problem for how to get the current, the voltage, everything in a three-phase transformer or three single-phase transformer. But before we do that, let's just have simple example here just to understand the connection. I will do only like part A. Well,
transformer just a little bit. Just a tad.
I'm trying to make it bigger. Can you see?
Yeah, can you just scroll the screen up just a little bit?
Oh, you want to write the other thing. All right. And then when I download this document, as I show, I have a table showing the all connection and the relationship between the voltage and the current line to line in all connection, delta, star, delta, and all. Very simple. Okay. So let's just look at this example. Very simple example. Three-phase transformer bank consists of 3 single-phase transformer, 12 turns ratio. And when we say 12 turns ratio, it doesn't mean A. It could be 1 over A. Just say turns ratio is 12. Because we don't know the standard of each body. Maybe somebody say turns ratio N1 over N2. Somebody will take N2 over N1. But our turns ratio that we agree about, that's N1 over N2. So we'll continue. So I will not write A equal to. Used to step down. All right, so step down. The voltage of three-phase 6600 voltage transmission line. So it's stepped down. So I have a transformer. And the voltage at transmission line is equal 6600 voltage. That's the high side. And that would be the low side. If primary line current means here 10 amp. So they want the secondary voltage and the line out current for Y delta and delta Y connection. Let me just take Y delta connection. All right. So we need to find the secondary line voltage. How we find the secondary line voltage, by the way, secondary line voltage. Remember, the turns ratio here given for the single phase. So that's the first thing you have to think about. Is A equal 12 or A equal 1 over 12? That is the question. Our A, N1 over N2. If it's step down means N1 greater than N2, right? Like if you want to visualize, N1 is step down, so N1 is like 100, the other one be 10, so it will be like 10. So A is big number when you have step down. Fraction F step up. So put this in your mind. According to A equal N over N2. You got it? All right. So according to this one, it's step down. So it's 12 or 1 over 12? 12. That's the first trick. If you don't understand it, tell me and then repeat again what I said. You got it? All right. So A is equal 12. And the question, I want to find the secondary line voltage. And this is a star delta. We already proved. We proved something that A, which is A square root 3 is equal V1 over V2. And this is line voltage. And now A is equal 12. So I'll say 12 is square root 3 is equal to V1. V1, the line voltage, is it given or not given? This is a transmission line, 6,000. All right. So if you want to find the line, that's star. What is this value? That's V1. That's V1. So V1 is equal to 6600 voltage. Why I choose V1? Because usually when you have a three-phase transmission line or three-phase system, when they give you the values, it's always line to line or line. That's, I mean, why they are going to tell you per phase. The only thing given per phase for a three-phase system, impedance. That's per phase. So that's V1, which is equal to, okay. And V2, the unknown one. So we want to find the secondary line voltage. It's very simple now. So V2 will be equal to divided by 12 square root 3. And you get the voltage. I think will be equal to 317.55 voltage. Okay, that's the first thing. We need to find the line current and the output. The line current, I have the same, the equation we got. I will just continue. It's equal I2 over I1, right? Or was the current opposite to voltage? And you want the line current and the output. Forget about this one. I'm now line current. Line current, you got I2, I1. You can get anyone. But it gave you if the primary line current is 10 amp, well, primary means I1. So it's telling you if I1 is equal 10 amp, what is the I2? Well, very simple. I'm going to use the same equation. A square root 3 is equal I2 over I1. So A is equal 12. Square root 3 equal I2. I want to get it. I1 is equal 10. So I2 is equal to 10 times 12 root 3. That will be equal to 207.84 amp. So I get both quantities of voltage and the current on the secondary. Okay. Very simple. So what is the other questions? Find the output kVA, the output apparent power. How you find the apparent power? S, if you know S in general, S in three phase. How you find S in three phase? Yeah, we did that the first thing. S, anybody know apparent power? Yes.
So can't you just find it like you would in single phase and multiply it by square root 3?
You can, but I mean, why? And you already have V2 and I2 and all line quantities.
So can you just do it like the regular way with the three phase?
Oh yes, tell me about the regular.
Well, I mean, it's just P plus JQ, right? So
Yeah, but I mean, you don't know P, you don't know Q.
yeah.
You want to get all of it. So how can you get the apparent power in terms of voltage and current?
Well, I mean, can you calculate P and Q based off of like, I think like V, RMS or I?
Yeah, but I mean, why I mean, you bother yourself? You didn't ask for P or Q. You asked for S as the quantity apparent power.
Yes, I'm just trying to find a way to get to it. I mean.
Okay, I'm giving you a hint. You have voltage, you have line to line voltage, and you have line current.
You can just be I conjugate, right?
Well, that's right. You multiply the voltage by I conjugate, but that's single phase. If you want to do it with three phase, you multiply it by square root of 3.
So just square root of 3.
Times, yes. Yeah. And even I'm not going to bother with the conjugate because they didn't ask about power and Q. They ask only about apparent power. So let me just what he said. S in general is in it's equal V I conjugate and a three phase. But if you only interest in magnitude, that's enough. But you have to remember, I'm talking about line. If you talk about phase, magnitude only, you don't use the vector. So I'm going to use the easy way. They didn't ask about power, reactive power, just you want the rated value. And also the rated value, like I mean, the transformer was 10,000 kVA. That's the apparent power. So I'm going to use this one for the that's for three phase. So I'll say S for three phase transformers equals square root 3 line voltage V2 I2, and I got V2 317.55 voltage, and the current it was 207.55, I think. No, 84. So that will be the apparent part in VA. If you divide it by 1,000, then you can get the in KVA. So that will be 114, I think. KVA. Yes. To get it in kilo VA.
Okay.
Yeah, that's it. So that's, I mean, it was a simple question, just how to calculate the value for three-phase transformer. So we learn how to find the turns ratio line to line, and how to find voltage or current using the turns ratio. I will call it, I mean, three-phase turns ratio using the single-phase turns ratio.
And we're using B2 and I2 because it asks for output, right?
It's out, yes. Okay. Yes. And they ask about the out. If you look at the question here, the output KVA.
Right. That's
Yes.
what I was just.
That's, yes, you're right. Okay. Well, how to analyze the circuit? It's really important. Very important. I'll be lucky if I finish only explaining this example, but it's important, and especially for those that are going to study power, it's the whole system. Just let's read the problem and see exactly what they ask for. A delta Y connected three-phase transformer. Okay, delta Y. Well, I'm interested to do Y delta. I want to show you on Y delta first. So let me get you another example, and then delta Y for you to find. So I'll give you a different example, and I'll leave you that as exercise, because I just explained to you how to find A for Y delta. So I'm going to use the same information, not to distract you to another thing. So the problem is like that. You have a transformer. I do it like that. I call it one line diagram just to make everything easy. It has high voltage side and low voltage side, and it's connected Y delta. All right. There is a bus bar here. There is a feeder connected to the supply. So that's the supply, and the supply connected to the transformer through a feeder. And feeder has impedance 0.8 plus J 0.5 ohm. And this is, of course, ohm per phase. You cannot have, okay. And the transformer, it's three single-phase transformers. So let me just make something here to make it clear. Each single-phase transformer, 10 kVA, that is the value, and 1,330 over 230 voltage, 60 hertz, and the equivalent impedance of this transformer is equal to 0.12 plus J 0.25. So that's the information of the transformer. We'll continue. Now, the secondary side, or the low voltage side on delta, there is a feeder that connected to load. And this feeder, so we have in this is in a complete real system. Source, feeder, connector, yeah, means connecting the source to the transformer. And then the transformer output connected to the load through another feeder. And the load is three-phase load, 230 voltage, 270 kilovolts amp. That's the apparent power at 0.9 power factor. And the feeder has impedance equal 0.003 plus J 0.015 ohm per phase. Just, I mean, to make everything easy, I will call the impedance of the feeder, I call it ZF1 because inside one, because usually I like to refer to the primary by 1 and the secondary by 2. So according that the feeder on other side, I call it ZF2, feeder number 2, and that's load. The load is given. What is the problem now here? What try to find? It's a very practical problem. You have load connected to the feeder, to the transformer, and transformer connected to the source. And that's the requirement of the load. On the consumer side, said I want this voltage to my load, I want this power, and with power factor, everything. So asking the utility, adjust your system so I can get the requirement of my load. So now what's required? To find the voltage of the source, that it will satisfy the requirement of the load. That's very simple question. So determine VS. To do that, there are certain steps. Obviously, I will not be able to complete the whole example, but I mean, I will I have to complete also in a video because it's very important example. If you understand it, I mean, that's it. I don't need any more example. That says everything. So the first thing, we need to find equivalent circuit of the system. Equivalent circuit. And the equivalent circuit should be like on high voltage side or low voltage side, doesn't matter. But what the first thing when I solve this one, deal with the transformer first, finish the transformer, and then go to the feeder and the load later. So that's the strategy to solve the problem. So I will say, okay, the transformer, get the whole information, find the equivalent circuit for the transformer. First, I have to know that A is equal to, I just write VB1 over VB2, just to remember, and to find the turns ratio. And it's given, what's VB1? 1000, 330 over 230, and I get the turns ratio, which is equal to 5.78. That's the first thing you do, turns ratio. Secondly, I want to find the equivalent impedance. So the equivalent impedance, you are dealing with Y delta. So I'm going to move everything to Y. I'm moving from delta to Y. So this equivalent impedance was given on the delta side of the transformer, bare phase. What I'm going to do, I'm going to move it to Y. So I will find Z equivalent 1. You don't remember formula. However, you want to have the formula sheet with you. But I'm just, for me, I don't have strong memory. So if I have the equivalent impedance on the secondary side 2, I want to move it to 1. So I'm going to plug the N1 over N2. That's what I do. I still do it till now. So I say Z equivalent 2 times N1 over N2 squared, which is the opposite of, no, N1 over N2 is equal A. All right. So I have A squared times Z equivalent 2. What's A? That's A. So I mean 5.78 square, and I have Z equivalent is given here, 0.12 plus J 0.25, and I get the Z equivalent, which is equal to 4.01 plus J 8.36 ohm. That's on the other side. Great. Remember, I know we did already the three-phase turns ratio, and we proved it's equal A square root of 3. We did that. And just let me refresh your memory, it's equal V1 over V2 and I2 over I1. And you can say that A for the, it's almost 10 when you do it, because it's equal this ratio. Let me just do it how I got A. So when you review, the A for a three-phase transformer is equal A square root of 3, and A, we got it here, equal 5.78 times square root of 3. That would be equal to, I found equal almost 10. It's like 10.01, something like that. So I make it 10. All right. So look what I did. Turns ratio, impedance equivalent, and the turns ratio of three-phase transformer. Now I'm trying to get to that. Let me just sketch what we got till now. I did the Z equivalent on the other side. So if we are talking about this side, I got the equivalent impedance, Z equivalent, one for the transformer. And don't forget, when you go to the line diagram, you have feeder here. The feeder here has impedance 0.8 plus J half. So I have another impedance here on the same side, which is feeder 1 on side 1, just to refresh your memory. Now I will do something strange and you can ask me and I will answer you. After that, I'm going to add both, which is logic. That's okay. So I will call it Z1 is equal ZF1 plus Z equivalent 1. To make it just add the resistance with the resistance, make it just 1. I did that, and that's equal to 4.81 plus J8.86. Oh, you'll find now I'm going to do something strange. After I did that, I'm going to move the all impedance to side 1, side 2, I'm sorry. Why? I'll tell you why. You have star and you have delta. And of course, I mean, you have feeder here. And you got feeder here and you got impedance. Already I make it Z1. I added all of it. It's all Z1. All right. I have two options. I move or ZF2 and the transformer or this one, I move it here. And the voltage, because I mean, there is load here. There's load. I mean, let me just refresh you. We have load here. And the load has a power factor. That's the issue that I found. That's the voltage of the load. And I have the current and power factor. When I'm moving here, so I have to find equivalent Y to delta first. Why? Because I want to make, I'm going to make transformer Y to Y. So I have to make the equivalent Y. When you make the equivalent Y, then you get in some hustle, you know, because the voltage here, that's here, that's line to line. When you go to delta, then you will go through angle shift and magnitude. You get just like in a big thing. Yes, you can say the voltage line here to find the phase, you divide by square root of 3, but what about the angle? What about the angle? Is the angle the same? No, there's shift 30 degree, 150 degree. There are many issues about that. And you have power factor, you have this angle. Maybe I forget, because usually I make this 0 and it's acceptable. And then let's say that 30 degree, I will have 30 degree. But if I move it by the same angle to the other side, there is a mistake and it will give you wrong answer. So can I do it right? Yes, I can do right, but it will take time because I have to go find the equivalent for delta here. To find the equivalent delta, I have to make the phase shift. I should consider phase shift. I'm not going to do that. What I'm going to do, I'm going to move everything here to this side, not to deal with the phase shift. That's why. All right. So let's continue. So just I explained to you why I have one. Why I'm going to move it to the other side to keep the load on that side with the all information. I don't want to change anything. Okay. Well, so now I'm going to, I have all this Z1 here on this side. And as I show you, I mean, I have on the other side ZF2, the feeder. But when you move Z1 here, it's going to be Z1 dash, right? So how can I do that? Somebody asked me when I did the terms ratio, say, why multiply by a square, divide by a square? He asked me the question, I answer him. I think you asked me about. And I told him the main thing, when you transfer one element from one side to another, to keep the power the same. That's the main issue. So what I'm going to do the same thing. Z1, I'm not going to use terms ratio. I'm going to use the concept. So that's Z1 I1 and Z1, and it should be here I2. So what is the power for the Z1 at this side? Z1 I1 square should be equal Z1 dash after I transform it, and the current there and the line current I2. So square. So what is Z1 dash? I will get the relationship. Z1 dash will be equal to Z1 times I1 square over I2 square. And now, what is I1 over I2 line current? Let me go to the turns ratio of three-phase transformer. That's the turns ratio of three-phase transformer is equal I2 over I1. I2 over I1. So that will be Z1 over A square, not the A of the single phase transformer, A for the three-phase transformer. So I have Z1, I have the magnitude is equal 4.8, 1 plus J 88, and divided by A square, which is 10 square, 00481 plus J 0.0088. So I got this one here, I move it there. I have everything on the secondary side. I have everything. It's done. The problem is done. But it is. What I'm saying, it's very simple now. I have everything on the other side collected on one side. That's it. Z feeder 1, 2, everything. But pay attention to this. I moved first. I mean, in single phase transformer, I move it to the other side to add it to the feeder and then get everything back to the load side. Why? Because I don't want to deal with the phase shift. What's left is simple. I will continue solving the problem. I mean, in this document and all upload. But that was the important thing. And after you see the solution, try understand it and then solve it by yourself.